Okay, guess we can start. So let's start with a recap of what we have from last lecture. In the last lecture, we have been talking about the probabilistic formulation of latent factor models. In the application of recommender system, we say that in recommender system, when we formulate it as a matrix factorization problem, this is the rating from user X to item I, and this is the factor for user S, and this is a factor for user for item I. And basically, this is actually a rating matrix factorization problem where you factorize the large rating matrix R into two matrices P and Q, and we have the regularization term, which is here, and we say that this is actually the length of each vector for each user and each item, and this is the most commonly used matrix factorization objective function, and it has done a lot for the Netflix prize. And we say that this is actually can be formulated as a probabilistic matrix factorization where you assume each user has a factor with a prior distribution over a standard Gaussian distribution, and each item J also drawing its latent factors from a standard Gaussian distribution as a prior, and we have this rating R that draws from a Gaussian distribution centered at the inner product of their corresponding latent factors. And if you write down, basically you take the product of these three Gaussians, and take the log, that will give you the objective function in here. Okay. And so this is probabilistic matrix factorization, and we kind of generalize from this probabilistic matrix factorization and say that we want to incorporate the content information from the items, and the best way and the most general way to incorporate this is through deep learning. So we kind of generalize the probabilistic matrix factorization into collaborative deep learning, where you have a deep component up top here to extract the compact feature for you and use it as the prior for the item latent factor generation. We say that this deep component and the graphical component, which is the probabilistic matrix factorization, can help each other and significantly improve the performance. And similar to the probabilistic matrix factorization, we can take the product of each term of the conditional probability, and then we can take the log, and this gives us the final objective function. And if you take the lambda s into infinity, this term will disappear, and we will reach a simplified version of the objective function. We also talk about a neural network perspective of the models. Basically, if you take the lambda s into infinity, that will be equivalent to simultaneously training two neural networks with a common input but different output. So the first branch will try to recover the content. The second branch will try to predict the ratings. Okay. So this is what we have from last lecture. So in this lecture, we're going to talk about something different, which is kernel methods. Kernel method, I think it's a very old but very classic type of method, and it's useful even for today because it has nice connection to neural network and deep learning as well. And in fact, there is some recent research using kernels to analyze the training of deep neural network, for example, neural tangent kernels. But we're not going to talk about that advanced topic today. We're going to talk about some basic ideas of kernel methods. And if you're interested after learning these materials, you can go back home and search for some state-of-the-art analysis of neural network training using neural tangent kernels, for example. Yeah. So kernel methods. Before starting with the kernel methods, let's talk about what we have learned before. What we have learned is, I hope you remember in the first few lectures, we talked about linear discriminant analysis. And in linear discriminant analysis, basically for each class of data, we try to learn a discriminant function, right? And in the Gaussian version of the linear discriminant analysis, for each class of data, we try to learn a Gaussian likelihood, right? So basically, for each class of data, we will fit a Gaussian with a different mean and different covariance matrix, and then we're going to get a corresponding covariance, corresponding discriminant function for each class. And this is the learning part. And when you're doing prediction, you will simply compute the value of the discriminant function for each class. Right? For example, you have two classes. You're going to compute the value of the discriminant function for class 1 and compute the value of the discriminant function for the second class, and then compare them. Whichever have the largest value, you're going to classify this data into that. You're going to classify that data into that class. Right? And again, if it's just a two-class problem, then basically you can take the difference between these two discriminant functions, right? You can take the difference. For example, you can compute G1 minus G2. We can compute G1 minus G2, and if G1 minus G2 is larger than 0, then you're going to say that this is class 1, right? Otherwise, you're going to say it's class 2. So this is what we have. And remember, we discussed 3 different cases for linear discriminant analysis. We'll talk about the easiest case is that we can learn a mean for different class, but their covariance matrix are shared, and also their covariance matrix are actually fixed. It's a fixed and diagonal covariance matrix. This is the first case. The second case, we say that each class can learn its own mean, but the different class, their covariance matrices are still shared, but the covariance matrix can have arbitrary shape. And the most general case, the third case we talk about, is each class can have its different means and also its different covariance matrix, and the covariance matrix can have different shape. So basically, for each class of data, you learn its own mean and its own covariance matrices, and this ultimately will give you a quadratic form of the discriminant function. So this Gi of x is the discriminant function for class I, right? And we see that this is a quadratic form. This is the second order, the first order, this is the 0th order. And remember, at the end of that lecture, we have some example that if we use this kind of the most general form, it can actually give us some very nonlinear decision boundary. For example, the decision boundary can be a pair of hyperplanes, like this, or it can also be some kind of hyperparaboloid, right? To the left is positive, to the right is negative. It can also be some hyperellipsoid, something like this. Inside the ellipsoid is negative, outside of it is positive. So it can have different shape. So that means linear discriminant analysis can actually give you nonlinear decision boundary. So this is what we have here. Basically, you're going to compute for each linear discriminant function has the form. Therefore, their difference G1 of x minus G2 of x also has this form. And this is actually equivalent. So basically, if it's a two-class problem, it's equivalent to learning a matrix W and a vector W and a scalar value W0, such that this one will form a decision boundary. Right? So this is linear discriminant analysis. So you can see that this is actually the function is no more linear. The function, the decision function, is actually a quadratic form. But one question from this is that can we do this in a linear way? So can we try to transform the original feature into a higher dimensional space, into a different space, and then if we do linear decision boundary on this transformed space, can we get similar result? Right? Can we have the same performance as linear discriminant analysis? If this is doable, then it would be great, because learning a linear model is much easier and it's much more computationally efficient. Right? And we actually have done this before when we talk about linear regression, or we talk about different basis function. Before we do linear regression, we will transform the feature using some basis function, for example, polynomial basis function or Gaussian basis function. And in this lecture, we call this radial basis function. So basically, in a polynomial function, given a feature, given a raw input x, right? The raw input x is only a scalar, right? It's 1 by 1, and we're going to use if we're going to use polynomial basis function to transform it into a higher dimensional space, it's going to become something like the first dimension is going to be 1, second dimension is going to be x to the power 1, x to the power 2, all the way to x power of n, something like this. So given only one scalar, we can do some kind of pre-processing to transform this original feature to original input to the feature space. Right? So this is polynomial basis function. We can do a similar for radial basis function. Right? For given only one x, right? You can have compute the value of different Gaussian bases. Right? For example, here we have 9 Gaussian bases. Therefore, given an x, you're going to compute the first entry is always going to be 1, right? And you have 9 other values corresponding to these 9 basis functions. So that's how you expand the original input into a feature vector, right? And then you can try to do a linear modeling on the transformed feature space. And to give you more intuition, let's take a look at this example. Let's say that in the regional space, we have the positive class. In the middle, we have the negative class on 2 sides. Right? Now, if I ask you to learn a linear classifier to classify the positive and negative classes, there is no way that you can do this like perfectly, right? Because there's no linear separator that can separate these 2 classes of data. But if you use radial basis, this can be done. Specifically, if you use 2 radial basis function, you set 2 Gaussian means, one in here and one in here, and then you transform it using the Gaussian basis, right? So basically the first dimension of the feature will be computed using e to the power of s minus mu1 square over 2h. H is something that you can set. For example, you can set it to 1, no problem. But the important thing is the mu1 here. You choose mu1 to be somewhere in here. Right? So basically, for each x, you're gonna compute phi 1, which is first dimension of the feature vector, and you can similarly compute the second dimension of your feature using a different mean. Right? This is mu2. Right? Mu2 is here. And that way, basically, for each point in here, you can compute phi 1 and phi 2, right? And transform it into a different position in this feature space. Right? And after you transform all these points into the feature space, you can see that there is actually a linear separator that can separate the positive data from the negative data. Right? So this is good. This gives us some hope that it's actually possible to transform the data from the raw input space to the feature space, and use a linear classifier to classify this data. Okay. Before I move on, I would like to see any question for this. Okay. This is actually similar to one of our examples several lectures ago. Hope this is clear enough. So the point is, sometimes the data is not linearly separable in the original space, but we can transform it into the feature space, and in that feature space, data are actually linearly separable. Okay. So after the transformation, the model becomes linear in the transformed features, and then we can apply all the previous tools for linear classification. Right? So question is this a reasonable approach? Yes, because we can always use functional approximation using basis function. It makes sense, right? And another reason that this is a useful and reasonable approach is that when you are able to transform P trains and light into a higher dimension, there's a higher probability that there will exist a linear separator to separate positive data from negative data. So this is called the Calvert's theorem. Formally, the theorem states that the probability of having endpoints linearly separable tends to 1 if your feature space has the dimension of your feature space is large enough. Right? For example, if your dimension of your feature space is very, very large, then you're in a good shape. Maybe most probably you're gonna have a linear separator that can separate the positive data from the negative data, no matter what the label assignment are. So we're gonna provide more details, basically provide more details on the theorem. But before going into detail, let's have some assumption of the theorem. The theorem actually assumes that this endpoint has to be in the general position. So what's general position? Let's say that we have 3 points, and it's in the 2-dimensional space. So in this case, if all 3 points actually they're on the same line, then this is not a general position. But this is a general position. So the theorem considering a case where no L1, no L plus 1 of these points can lie on an L minus 1 dimensional space. So to make this easier to understand, so here we have a very specific example, n equals to 3, L equals to 2. So basically, no L plus 1 is 3. No 3 points can lie on a L minus 1. So L minus 1 is 1. Right? So no 3 points can lie on a 1-dimensional space. So this is not a general position. This is a general position. So the theorem's proof based on this assumption. And then let's present the theorem. The theorem considers this case. In its whole, the more formal version, we're going to talk about the formal version, and then we're going to talk about the version that's easier to understand. The formal version says that the number of groupings that can form in a L-dimensional space by L minus 1 dimensional hyperplane to separate these points into 2 classes. This is the number of groupings. But what does this mean exactly? So let's take a look at this example. Let's take a look at this example where you have 4 points, and you're in a two-dimensional space. Right? So this is 4 points. Now we're going to draw these 4 points on the blackboard. Okay, so this is 1 point. Another point is here. Another point is here. Another point is here. Okay. So we have 4 points, and we're considering a binary classification problem. So each of these points can either be positive or negative, right? Therefore, there is actually 2 to the power 4 configurations of labels, right? So this point can be positive, negative. This point can be positive, negative. Therefore, there will be 16 possible label configurations. Now, the question we are considering is, among these 16 label configurations, how many of them can be linearly separable? For example, let's say that you have this point is positive, all the other is negative, then naturally you can have a linear separator here, right? And if you flip the label, this is negative, this is positive, 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 you can still use the similar linear decision boundary, right? Only you need to flip the labels. So what are the cases where you cannot have a linear separator? Anyone? You mean this, right? Yeah, exactly. So basically, if you run into this case, for example, this is positive and this other 2 is negative, then there's no way you can create a linear separator to separate the positive from the negative, right? And similarly, you can flip the labels. You can flip the labels that this is negative and this is positive. In this case, similarly, you cannot have a linear separator to separate them too, right? And this is actually the only 2 cases where you cannot have a linear separator to separate positive from negative. So all the other configurations, you can actually separate them. Therefore, among 16 configurations, there are 14 of them that is linearly separable. So in this case, you're gonna see that if you are running into a problem where you have 4 data points only and it's 2-dimensional space, then there's a high chance that you can have a linear model to classify the data really, really well. Right? So this is what this theorem tells you. The theorem provides this equation to tell you how to compute this 14 here, basically. So if you compute this number, you're going to get 14. How do you compute this? So basically, it's 2 times what? 2 times n equals to 4, right? So n minus 1 is 3, and let's do 3 choose 0, and then 3 choose 1 plus 3 choose 2. Right? L equals to 2. Right? So basically, this is going to be 2 times any number that choose 0. You have only one way of choose 0. This is 1, and 3 choose 1 is 3. 3 choose 2 is also 3. So basically, this is going to be 14. Right? So using this equation, you can compute how many configurations can be linearly separable. So this is what the theorem tells you. And if you think about the probability, like this one, right? If you think of the probability, and the probability that you're going to run into the case where it's linearly separable is O and L. So this is the original O and L that we have. O and L over 2 to the power of n. So O and L is 2 times something. Right? Therefore, we can kind of cancel out the 2 in both the numerator and denominator. Therefore, this is what we have. So this is the equation to compute the probability that these endpoints are linearly separable. And if you take a closer look, you can see that this is actually the probability of you flipping n minus 1 times of a fair point, and you end up having L, or fewer of them are heads, right? So this is what you basically, this is exactly the probability. And if you plot them in a figure, so let's say that the horizontal axis is the ratio of n, the ratio between n and L plus 1, okay? And here, the vertical axis is the probability that they are linearly separable. And you can see that as the ratio gets larger and larger, the probability gets lower and lower. So the ratio getting larger means that it's more, the space is more densely populated, right? Because the ratio, this is the ratio between n and L basically. So if it gets larger, then you're in the same space, but you have more points, right? Therefore, you have lower probability that they can be linearly separated. And there's a kind of like a critical point here. The critical point is the ratio is 2. At this point, it drops very dramatically. Right. So here, but if the ratio is very much lower than 1, then there's a very high probability, right? You can separate the positive from the negative. Okay. So this is the consequence of transforming data to a higher dimensional feature space. Right. Any questions so far? Let's see. I think this is more like if you are using you're using L1 regularization and L2 regularization. But we're not going to talk about this in this figure. For now, you only need to know that this is just a trend of you going from very sparse space and very crowded space. Okay.
So the L1 is the regularization, right?
Mm-hmm. L1, L2, let me see. Yeah, I guess for now you can think of it as a different regularization. Or another way to see this is you can think of it as different cases in the reality. For example, we are talking about the case where you every point has to be in a general position, but there is some extent that this assumption actually doesn't hold, and this is the extent that this assumption doesn't hold. And yeah. Okay, any questions? Okay, so this basically tells us that you can transform the feature from the original space to a higher dimensional space, and you get a much higher chance of making them linearly separable. And basically, the probability of having endpoints in the linearly separable classes tends to 1, right? Provided that you have larger L, much larger L than N. So this is very intuitive. And so this tells us, right, by mapping a high dimensional space, we can increase the probability of linear separability. So provided the space is not dense too densely populated. So the space is not too densely populated, meaning that the ratio is not too large. So this is good news. This provides us hope that we can actually transform into high-dimensional space and do a linear model. And we can actually have some kind of a constructive proof to show that it's actually to find this kind of mapping. The constructive proof shows that for any set of endpoints, that it's possible to design a mapping from the original space N, capital X, to a feature space F such that all these points in the feature space are linearly separable. So the constructive proof is that we can map these endpoints from the original space to a simplex of n-1 dimensional space. So to give you an example, let's say that you have 3 points, right? You have 3 points, and then you can map it to a triangle. Right? The triangle is a 2 dimensional simplex. So if you have 3 points and you have a transformation match function to transform it into the feature space and make it look like this, then they are linearly separable for any label configuration, right? Because for any configuration you can like have a linearly separator to separate them. And a simplex is actually, you can think of it as a generalization of the notion of a triangle or tetrahedron in an arbitrary dimension. So this is a 2-dimensional simplex, right? If it's 3-dimensional simplex, then it will be like a pyramid, right? You can think of a pyramid, and no matter how you configure the label, there is always going to be a hyperplane that can linearly separate the positive from the negative, right? So this is the pyramid is a 3-dimensional simplex. Basically, you have a triangle, and you place all the points at each vertex of the triangle, and then you can ensure that they are always going to be linearly separable, no matter how you configure their labels. Okay. Any question for this one? Okay. So this is another form of Carver's theorem. So the problem with this kind of generalized linear model is the curse of dimensionality. Specifically, let's say that you are given a lot more features. In the polynomial case, right? In the polynomial case, we say that if we are given 1-dimensional feature, and if we do a quadratic feature expansion, then we're going to get the first dimension is here, and the second dimension is x, and the third dimension is x squared. Right? So this might not seem too bad because you have 1 dimension and you expand it to 3 dimensions. This is okay. However, if let's say that you have your original feature is a 2-dimensional feature, x1, x2, and then you're going to use quadratic expansion. What's going to happen is that, first of all, you're going to have term 1, right? And you have the first order term x1, x2, and then you're going to have another term which is x2 times x1, and then you're going to have x1 squared, and then you're going to have x2 squared, right? So basically, the dimension of the expanded space, if you use quadratic expansion, is going to be, for example, this is m, then the dimension of the feature space is going to be m squared. So once your original space has a relatively large dimension, the expanded feature space will have a much larger dimensional space. And this is a bad thing, because if you have a very high dimensional feature space, it's very easy to overfit, right? Because imagine that you have only 100 data points. 100 data points. So n is 100, and each data point each data point you have 50 dimension, so D is 50. Right. If you're in this original space, then there is a good chance that you can do a good job in terms of classification. But if you expand the feature into a feature space using quadratic mapping, then in a feature space you're going to have 100 data points, but you're going to have a 2,500 dimensional feature. So this is very easy to overfit because your dimension is much larger than your data points. Right? So it's very easy to overfit. So this is a problem. The problem is that if you naively expand your feature, then that might not work. Okay? So one way to do this is to use to avoid this kind of simple quadratic expansion, a polynomial expansion. Instead, you focus on you can use Gaussian basis function. In Gaussian basis function, the number of dimensions in your feature space only depends on how many basis function that you use. Right? For example, you can use 4 basis function. Right? If you use 4 basis function, then no matter how large your original space is, because your original space can be 10 dimension, right? But if you use 4 basis function, then your feature space will only have 4 dimensions. Right? So basically, you're going to have, in this example, you're going to have 4 basis function. So this is the 4 basis function. Fn of x means the nth feature in your feature space, right? And in the way that you compute your nth feature is to have a center Cn, and this is the standard deviation, right, for the nth feature. Basically, you're going to plug x into this equation and compute the nth feature. And this nth feature, it's a scalar value, right? So basically, if you have 4 basis function, you're going to have 4 dimensions in your feature. And then you can learn a linear model on top of your transform feature here. Right? This is a linear model. Wn is another scalar. Right? Okay. And this g of x can be your final classifier or the discriminant function. Right? And this is one way of avoiding this kind of curse of dimensionality. So let's take a look at an example that actually do use Gaussian basis function or radial basis function. Let's say that you have only 4 data points. Right, this is 4 data points, 0, 0, 1, 0, 1, 1, and 0, 1. You have 4 data points. And this is class 1. And on both sides, they're class 0. And then we're going to use 2 radial basis function. Right? Originally, it's not linearly separable, as we discussed before. Right? So how do we make it linearly separable? We can use radial basis function. So we're going to use 2 radial basis function. Right? C1, C2 shows 2 centers for this 2 radial basis function. And for simplicity, we're going to set sigma 1 and sigma 2 to 1 over the square root of 2. So basically, it's just some simple number. And then this way, you can kind of directly cancel out the denominator here. Right? Therefore, given the original input x, the new feature y, will have 2 dimensions. Right? The first dimension will be the exponential minus the square distance between x and c1. Right? C1 is the center for the first basis function, right? And the second dimension will be exponential of minus the square distance between x and c2. C2 is the second center. Right? So for any x, you can compute the corresponding 2-dimensional features using this equation. Right? And what it looks like is you have something like this. For 0, 0, you plug it into this equation, and you get this new feature vector. Right? For 1, 1, you get this feature vector. And for 1, 0, and 0, 1, you get something like this. So interestingly, these 2 points actually they have exactly the same feature space, position in the feature space. Now let's draw it in a figure. So this is the original space, right? This is the original space, and this is how to map it into the feature space. This is y1, the first dimension of the feature. This is y2, the second dimension of feature. Right? So you can see that these 4 points are mapped into here. There are 2 points that are overlapping in here. Right? So basically, after you map it into the feature space, you're going to see that they're actually linearly separable now. So the linear separator, one of the linear separators is this linear line. Right? So we can have a linear decision boundary, and this line is y1 plus y2 minus 1 equals to 0. This is exactly the line here. And what does it mean? It means that you can, for any points, for any new points, you can compute its y1 and y2 and compute g of y to see whether it's larger than 0 or smaller than 0. If it's larger than 0, then it's positive. If it's smaller than 0, then it's negative. Right? And interestingly, you can also plug our radial basis function into this equation. y1, remember y1 equals to the exponential of minus L2 square of x minus c1, right? So we can plug all the radial basis function into this equation, and this is what you get. So this one is your decision boundary in the original space. You can see that C1 and C2, they are given. Right? X is the variable. Right? X is the only variable in this equation. So this is a decision boundary. If you draw it in the original space, this line looks exactly like this. So this is a nonlinear. This is a nonlinear decision boundary, right? So if you have the right basis function to expand the feature or transform the feature, then you can actually do a very good job. Any question for this part? Okay. So here we are kind of have some fixed centers, right? So we look at the data and we know that which center should we choose to do the use as a radial basis function. In practice, you might not have this luxury, but still, you can try to. One way to do this is that you can plot the data, and you look at the data and choose the centers for the radial basis function. Another way is to randomly choose the center for the radial basis function, as long as you have a large enough number of radial basis function. As long as, for example, if in this case you can randomly choose some radial basis function, randomly choose some centers. As long, for example, let's say that you can choose 10 centers, but as long as, for example, 2 of the centers are very close to these 2 centers, then the data will still be linearly separable. Right? So this is a discussion of how practical it is. We can always choose center randomly among the data points, and then you can fix the standard deviations, like what we do previously, and then you can learn a linear classifier. So this is what you do if you want to avoid this kind of quadratic expansion. And another thing is that instead of randomly choosing the centers, you can also do kind of like EM update. We call it as basically alternately update the linear classifier and update the centers. But this is a nonlinear approximation task, So we're not going to talk about this in detail. So, and this part, up until now, this is the feature expansion plus linear classifier, and the point of this part of the material is to show you that it's sometimes very beneficial to transform the data from the input space to a feature space, because sometimes the data is not linearly separable in the data space, but it can be very, very well linearly separable in the feature space. And this is kind of a very important point of kernel methods, because what kernel methods do, you will see later, is actually sometimes it's kind of like being able to transform the data into an infinitely many dimensional feature space using a very efficient way. We're going to talk about this later. So for now, let's start with our gradual introduction of kernel methods, and where does it come from and why is it useful. Let's look at this slides line by line. Okay. For the first line, in this lecture we're gonna focus on the regression problem. Specifically, we're gonna focus on the linear regression problem. So in the linear regression problem, we have some data, and we want to learn a linear, kind of like a linear model to predict y given x, right? So here we have n data points, right? And phi of Sn is the feature for the nth data point, and w, so this is a n-dimensional feature, right? And w here is a m-dimensional weights vector. So this is the model parameter that you're trying to learn. And Tn is the target for the nth data point. So this whole thing in the first term is the error term, right? It's the square error of your prediction. Your prediction is the inner product between w and phi of xn, right? And your ground truth is t of n. And therefore, the first term here is your error term, and the second term is your L2 regularization to prevent the model from overfitting. Right? So this is the linear regression model. So far, any questions? This is what we have learned like several lectures ago. And then, if you think about what we have been doing to get the optimal parameter w, right, given this objective function, what we have been doing is that we say there are two methods, right? The first method is to compute the gradient and use gradient descent. Another method is to compute the gradient with respect to w and set the gradient to 0. Right? So let's first take a look at the second method. Let's first look at this objective function, and then we're going to take the gradient with respect to w and set it to 0 and see what happens. So if we do this, then what's gonna happen is that in the first term, we're gonna have something like times 2 times this is the sum, right? And so we're going to use train rule. This one minus this one. And the train rule says that you need to, let's say that your error term, the whole error term, the error term is let's denote the error term as ERR. Then the gradient of the first term with respect to w would be the error term's gradient with respect to might be something like this. How about let's do this. If you have a very simple error term, w x minus t n square, then you can compute the gradient with respect to w using train rule by doing this, right? Minus t, and this is the gradient with respect to w. Right? So this is one of the term, right, in the sum of error, right? And we're computing the error term, right, with respect to w. So in here, the first term, the first small term, is actually 2 times this whole thing, right? So 2 times w minus tn. Right? So this is the first term, first subterm, and the second term, the second term, this is actually the linear form of w, right? And it's irrelevant to tn. Therefore, the gradient in the second subterm is actually phi of xn, right? So this is the gradient with respect to w for each error term for each data point. Right? And then if you add them up, so basically you can add them, right, for n from 1 to capital N, and this is what you have. Right? Have something like this. Right. So this is going to be your gradient for the first term, right, for the error term, and then you're going to have the second term, right? The second term is here, the regularization term. We're going to compute the gradient of w, right? Gradient of this second term with respect to w, and this is a quadratic form. Therefore, the gradient would be 2 over lambda times 2 times w. Right? So this is the gradient for the second term. Okay? And then we're going to set it to 0. After we set it to 0 and rearrange them, we're not going to get to something like this, right? Because we can put this to the left, right, and maybe divide it by lambda, and then we're going to get something like w equals to minus, because we're going to move this to the left, right? And then we're going to divide both sides by lambda, and what we get is minus 1 over lambda times this whole thing, right? This whole thing. Right? So this is what we have. This is what we have in here, right? And what's next is that if you look at this part, right, minus 1 over lambda is a scalar value, right? And this inner product between w and phi of xn minus tn, this is actually another scalar value, right? You can denote this. You can kind of denote 1 minus lambda times wn phi fn minus tn. You can say that this is, denote this as an. So an here is a scalar value here, and a scalar value. So kind of change the notation here, change the variable here. So this is an, and since you have capital N data points, you're going to have capital N values for this an, right? A2, A1, A2 all the way to A capital N. And then you can write this. You can write this one as a matrix form. So remember the size of the matrix here. So this an is 1 by 1, right? It's a scalar, and phi of xn, it's the n-dimensional feature, right? So this phi of m is an n-dimensional feature. Therefore, we can this one, if we denote a large matrix phi as phi s1. So this is the feature for the first data point, right? Feature for the second data point, all the way to the feature for the last data point. So each of this phi is actually n dimension, right? And you have n of this. Therefore, this whole thing is going to be n dimensional. It's going to be n by n, right? It's going to be an n by n matrix. So this is phi, and the phi transpose will be a n by n matrix. Okay. So basically, we can write this in a matrix form. Right. And A we denote A boldface A. So whenever we have boldface, it's actually a vector, right? So boldface A is actually A1, A2, all the way to AN. Okay. So this is boldface A. Therefore, this whole thing can be rewritten in the matrix form as the matrix vector multiplication between the feature matrix phi and the vector A. Right? So if you look at this, this stuff, you can see that the phi is already known. Right? The phi is actually the data itself, and you can see that what's unknown here is actually the weights here. Weight A here. A is unknown because A is some kind of a transformation of W. Therefore, you can kind of see what's going on here. What's going on is that if you try to optimize the original objective function to find the optimum of W, it's actually equivalent to finding the optimal A here. Right? So this is we call the optimization of the original objective. We say that we are operating on the primal space, and if you're optimizing A instead, and then maybe later you're going to transform it back to W. If you optimize A, then we say that you're optimizing in the dual space. So in the dual space, you can actually plug. Now you know that W is equal to phi transpose times A, right? You can plug this into the original objective, and this is what you get, right? The original objective is, again, if you look at the original objective, the original objective can be written in the matrix form too. Right? The original objective is basically just a feature matrix, right, times the let me see, times W. This is W square times the feature matrix. Right, the W square times feature matrix minus the vector. So this T is all the target value, so basically all the label for the n data points. So this T is the vector corresponding to T1, T2, all the way to Tn. Right. So you can write the original objective function as 1/2 times. So this is a vector. Okay, this is a vector now, and so you can, and then you can plug. You already know that W is equal to phi transpose times A, right? You can plug this W into this equation, right? And you kind of and you're gonna get this equation. you're going to expand this, because after you expanded this, you're going to get 3 terms, right? This is the 3 terms in here. 1, 2, 3. And the last term is just the regularization term. If you plug W equals to 5 times A, you're going to get something like this. Okay. So basically, we are transforming the optimization problem in the original primal space where we're optimizing W into a dual space where we're optimizing A here, right? And you can see that this dual space is also an objective function. And what's unknown in this objective? Phi is known, right? Phi is already known. T is also known. T is your labels for the whole data set. Right? So what's unknown is only the weight vector A here. So everything is the same. You just to solve this problem, you're actually solving a quadratic programming problem. You're just trying to find the optimal A such that this objective function is minimized. So this is no more different than the original problem. It's just you do some transformation, and that's it. So what's good about optimizing a dual space compared to optimizing in the original space? We're going to see this later. One thing to note is that if you look at this phi times phi transpose, it's actually a n by n matrix. And this n by n matrix, the nm entry of this n by n matrix is only depending on the inner product between 2 features. So what it says is that in order to construct this objective function, all you need is to compute a lot of inner products. Basically, this is all you need. All you need is to compute a lot of inner products and construct this matrix K, and then you can construct this objective function, and then you can solve this objective function. And this inner product, we can write it in a simpler form, which is K of Sn and Xn. Right? And this is usually called the kernel matrix. The matrix K is usually called the kernel. And you're going to see later why this is important. Okay, maybe in the next few slides. But for now, just bear with me that you can rewrite everything. You can rewrite this phi times phi transpose as a matrix K, and then you can plug K into this whole objective, and this whole objective, after you plug in K into it, will look like this. So this is still the dual objective, only that you're going to say that this one is actually K. Right? This is, and again, K can be computed, right? K is already known, T is already known too. What's left is A, right? So basically, in this dual objective, we're going to find A such that this objective function is minimized. Okay. And if you look at it carefully, again, minimizing this objective with respect to W is equivalent to minimizing this objective, right, with respect to A. Right? One difference is the dimensionality is different. If the n is the number of data points, m is the number of features. Right? If your number of data points is much larger than the number of features, then it might be better to use J of W, right? Because in this case, you have fewer parameters to learn. And if it's the opposite, right? M is much larger than n, then it might be better to use J of A, because again, these two problems, they are equivalent. Right? But if you use J of A, you have less parameters to learn. Then it's going to be more efficient for you. Right? So this is the first part of the kernel methods. Basically, we're just playing some linear algebra trick to transform the optimization problem with respect to W into another optimization problem with respect to A, right? And we make some change of variables along the way to basically transform the J of W into J of A here. Right. Any questions so far? So this is probably the very important start of the kernel methods. And whenever you think about kernel methods, this is the very first intuition of kernel method, and later we're going to talk about why is this useful. Okay. If you look at all this procedure, you're going to see that this is just some kind of simple transformation, and at least up in this point, you're going to see that these two problems, they're equivalent, right? And the only difference is how you solve it, but the end effect is the same. You're gonna get the same model, right? Because if you choose that's because after you're choosing a fixed feature space and everything will be equivalent. But the key here is sometimes you would choose a very clever kernel matrix such that it's actually equivalent to mapping a feature space that's in an infinite dimensional space. Before talking about this, let's first take a step back to see that if we solve the problem, let's say that we already solved this dual problem, and what's the solution for this dual problem? The solution for this dual problem is relatively simple because we're going to use our own old trick, right? Just take the derivative or take the gradient with respect to A and set it to 0. Right. It's very simple. And you're going to get the optimal solution for the dual problem. The optimal solution for the dual problem looks like this. So the K is the kernel metric, which you already know, right? In is the n-dimensional identity matrix. Lambda is the hyperparameter, and T is your label, right? Your label vector. So this is A. Then how do you predict Y then? So now that you have learned the model, right, given the new data S, how do you predict Y? Again, back to our primal space. In the primal space, we say that this is a linear model. Therefore, to predict Y, you just need to take the inner product between W and the feature phi of X, right? And then we say that, oh, this W is actually equal to A transpose times the feature matrix, right? So this is another transformation. And then if you look at this one, this is the feature matrix. This is the feature for all the data. This is the feature for this current data, right? And this is something that you can compute actually, right? This is something that you can compute. And it turns out that you can compute it very easily. The same way we define the kernel matrix, right? So this A transpose is here, right? A transpose is here, and this phi times phi of X, we denote it as both phase K of X. So both phase K means that this function is going to return a vector, right? This function is going to return a 1 by n vector, and so 1 by n vector. What's the first entry? The first entry is the kernel value, basically the inner product, right, between the new data X and the first old data S1. Right? And the second entry will be K of X S2 all the way to K of X and Xn. Right? So this is the definition of both phase K of X. Now that you can compute the both phase K of X and compute everything else, and you can actually compute the prediction, right? You can see that you can kind of see this as a weighted average, right? A weighted average of the original of the data points. Right? The K of X gives you the weight for each old data points, right? And the more similar you are to some data point, the weight will be larger, basically. So after you solving this dual problem, you can actually make predictions, right? Using everything that's ready. So any questions so far? So far, it's just some kind of linear transformations, okay? And this is kind of related to one of our previous slides. If you still remember, when we're talking about linear regression, we also talked about equivalent kernels. Highly encouraged to go back to the slides if you have time. So now let's briefly, let me see. Okay, let's briefly talk about, to motivate, because some of you might have this in mind. So why do we need to go through all this trouble, right? Why do we need to go through all this trouble to transform the primal problem into a dual problem? Right? Why do we need this kernel matrix representation? Remember that we say that this kernel matrix, the nth entry in the kernel matrix. So basically, this is the nth row, the nth column of the kernel matrix, can be kind of represented using k of xn and sm, right? So this is a function that takes xn and sm as input and outputs some scalar value, right? And defining it as the inner product of two finite dimensional features is just one way of doing it. We can actually use another way to define k of xn and sm. One way to do this is to define it as the exponential to the power of distance between these two. You can see that this one, if you look at this at first sight, there is no way that it can actually be rewritten into this inner product form, right? But we can generalize it. We can generalize this kernel matrix and say that forget about this inner product. All we want is the kernel function here, right? The k of xn and sm, and we define the kernel function as something like this. Right? This is sometimes called the radial basis kernel or RBF kernel, radial basis function kernel. Right? And if you look at this, so this is one way of computing the kernel value, right? Because this just take the L2 distance between these two axes, right? And raise e to the power of the L2 distance, right? So this is going to be a scalar value, right? And if you use Taylor expansion, you're going to see that this one is actually proportional to this one. So what's this one? This one is actually the sum of a lot of terms, right? From 0 to all the way to infinity. And in each of this term, you're going to have xn to the power of I times xm to the power of I. And the denominator is I factorial. So this, what this means is that this kernel value is actually equivalent. It's actually equivalent to the sum of infinitely many terms, right? And if you look at this, it's actually equivalent to saying that this kernel computation is like saying that the phi of xn is actually an infinite dimensional feature that where the first entry is 1, the second entry is xn, the third entry is x to the power of 2, of course divided by some value and all the way to xn to the power of infinity. Right? So if you use this kernel function, it's actually equivalent to expanding x into infinitely many dimensional space. Right? It's actually very cool. And when this is first developed, people call it the kernel trick because it looks very much a trick, but it's actually very, very helpful. Right? If you do this, it is equivalent to expanding the original input into infinitely many space. Right? And we know that if you have a higher dimensional space, there's a better chance that you can find a linear separator to separate the positive from the negative. Right? So this is the main intuition, the main reason why we need this kernel trick and why we need to transform it from the primal space to the dual space. So let's take a short break. For 10 minutes, and we're going to resume at 11:49. let's get started. Let's continue our lecture. So here, remember, someone is asking a good question. Will all the kernel function look like this? Since this is all just the inner product between two features. So the answer is no, because you can see that different kernel function can correspond to different phi here. The phi is a transformation matrix that transforms the original feature, original input, to the feature space, right? If you have a different kernel function, that's going to correspond to different feature mapping. Okay. So this is some kind of intuition on why we need this kind of kernel method or kernel trick. The reason is that we want to chiefly transform the data from the input space to an infinitely many dimensional feature space. And later we're going to talk about this in a more rigorous form and in a more general ways. Okay. Any question for this part? Okay. So this is a high-level introduction of kernel methods. So here are several interesting questions to ask about kernel methods. And moving forward is, the first one is, what's the computational complexity of doing things in the original space versus in the kernel space? Right? You can see that we have two objective functions, right? One is with respect to W, the other is with respect to A. And this can actually be very easily analyzed, because all of them, if you take the gradient and set them to 0, it's just a simple computation of how many computation, how in terms of like computation complexity, right? For example, if there is an operator that need you to take the inverse, that's going to be n cubic, and if there is a matrix multiplication, that's going to be n times k times m. I can easily analyze it. The second question is this form of solution just by accident, right? Or is it just specifically a choice of Bayesian linear regression that we have talked about, right? This is actually related to some of our previous slides when we are analyzing the Bayesian linear regression. There is connection, but not necessarily. And the third question is, how do we choose the kernel function, right? Like I said, different kernel function can correspond to different feature mapping, and it actually introduced different model specification or model inductive bias. Right? So how do different kernel functions affect the behavior of the predictors? We're going to talk about this too later in this lecture. And another question is, if we just specify, right, a kernel function, can we figure out what the equivalent feature mapping is? So this is like the reverse thing, right? So when we are motivating the kernel method, we go from the original space to the feature mapping and to the kernel function. Now we say that if we specify a kernel function first, can we figure out what's the equivalent feature mapping? The answer is also yes. Okay, so we're going to talk about this. Most of our second half of the lecture, we're going to talk about the last two questions here. So for this question, how do we choose kernel function, and do different kernel function affect the behavior of a predictor? All right. So before going to different kinds of kernel functions, let's look at this kernel in a more general perspective. Okay? This kernel is actually quote unquote, is actually a general name for a function of two arguments mapping a pair of inputs, right, x and s prime, into a real value. any function that's mapping two input from the input space to a real value, we can call it a kernel. And when we are talking about kernels in kernel methods, we usually refer to symmetric and positive semi-definite kernels. So what's symmetric kernel? Symmetric kernel means that k of xy is equal to k of yx. So this has to be symmetric. If you think about our previous case, we compute the kernel between x and y by computing the distance, right? We compute the distance between x and y, and then we compute the e to the power of the distance. So the distance doesn't really depend on the order of x and y. So this is symmetric. And the second one is positive semi-definite. So what's positive semi-definite? Positive semi-definite means that if you compute the integral, if you compute this integral, then this integral must be larger than or equal to 0 for any function. Okay? And this is the kernel function. And later we're gonna talk about it in a simpler and more intuitive way. So this is the kernel function, and remember we have a kernel matrix, right? So correspondingly, we have a kernel function, but in the context of a data set, we have a kernel matrix. If we have n data points, then we're going to have a n by n kernel matrix, right? The kernel matrix sometimes is also called a gram matrix, right? And the ith row, the jth column of the kernel matrix is computed as the kernel function of xi and sj. Okay, so and after computing this, you have the kernel matrix. And if a kernel function is a positive semi-definite, we usually call it PSD kernels, then any kernel matrix that is obtained from this kernel function is actually a PSD matrix. So what's PSD matrix? PSD matrix means that for any vector c, if you compute this value, so remember this is after you compute this one, it's going to be a scalar value. Okay, so let me. So let's say that you have 3 data points. So 3 data points. Then the kernel matrix is going to be a 3 by 3 matrix. And to say that this kernel matrix is a positive semi-definite matrix, that means for any C, so C should be a 3-dimensional one. This is C transpose. So this is C. You see, if you multiply them, this is going to be a value. Right? So given the matrix K, however you set the vector C, this value is always going to be larger than or equal to 0. If this happens, then you say that this kernel matrix K is actually PSD. Okay, so what's this then? So to give you an even more intuitive way of looking at this expression, it's actually equivalent to taking the sum of all the pairs of x and y, right? And in each of this term, inside the sum, there is the ith entry of C times the jth entry of C times k of xi and sj. Okay. And if you sum them all up, that's equivalent to computing the product of C transpose K times C. Okay. So this is a kernel matrix. Okay. So you can kind of see that this is the reason why we need this is like when you're computing the norm of a vector, the norm has to be larger than or equal to 0. Right? And this kernel is kind of like a transformation of the distance space. So naturally, it has to be larger than or equal to 0 as well. And let's go to the more general part. So we're going to talk about different kernels. So before talking about very specific and concrete types of kernels, let's talk about a very general type of kernel. One general type of kernel is called stational kernels. So what's stational kernel? Stational kernel is the kernels that the value of the kernel function only depends on the distance, the difference between the two values. If k of x and y only depends on x minus y, then we can actually rewrite it as k of x minus y, right? Okay? And then we can kind of denote. We can introduce a new variable called tau, and we can say that tau is actually equals to s minus y, and then we can rewrite the kernel function as k of tau. So for any kernel that depends only on the this difference between x and y, we call it stational kernel. And there's an interesting property for and by the way, the kernel we have been using, right? The motivation that we mentioned, the kernel. This is RBF kernel. RBF kernel is also a stationary kernel. You can see that it depends only on the difference between x and y, right? You just wrap it with the L2 distance and wrap it with another layer of exponential. So this RBF kernel is also a stationary kernel. So for stationary kernel, there's an interesting property. So the interesting property of the stationary kernel is you can do a Fourier transform for this stationary kernel. So this stationary kernel is equal to this integral here. So what's inside this integral? Let's take a look. So this one, the first part is e to the power of 2 pi times I times s times tau. So s here is the frequency. You can think of it as the frequency of the kernel function, of a part of the kernel function. And big S of small s is like the magnitude for each frequency s. So what this says is basically, so this e to the power of 2 pi I s tau is actually equal to cosine of 2 pi s s plus, this is the image, we're assuming a complex number here. This is the image plus sine of 2 pi s x. So this is the Fourier transform. So a Fourier transform tells you that you can actually decompose this kernel into a summation of a lot of these terms, and a lot of these terms but with different s. So basically you can kind of rewrite it as something like cosine and 2 pi sx times sine 2 pi sx, and you're gonna sum them up basically. So this is s equals to 0 all the way up to s going to infinity, and you have different s's. So it's like this. If you say that this is a kernel function, then this kernel function can be decomposed into this one plus this one plus this one, something like this. So it's going to be infinitely many terms, and you sum them up, and this becomes a kernel function. So what it says basically is that the kernel function is sometimes it can be a very highly nonlinear thing. It's more than just what it looks like. And this s, big S of small s, we call it spectral density. Right? That basically is the magnitude of the frequency s. Right? So if you're familiar with Fourier transform, then this S of x basically tells you how much power you have for each frequency. Okay, and this is Fourier transform, and this is actually the inverse Fourier transform, right? To give you the spatial density. The point of this slide is to tell you that usually a kernel function can be decomposed into the sum of a lot of terms, right? This is actually consistent with our previous intuition, right? If we define this kernel function, then this kernel function can be decomposed into a sum of infinitely many terms, right? So this is just and we know that this RBF kernel, right, is actually a special case of the stationary kernel, right? So this decomposition is actually a special case. You think of it as a special case of the Boltzmann theorem. Okay. Any questions so far? Okay. So this is stationary kernel, and inside the family of stationary kernels, we have a even more special case. The more special case is that if the kernel not only depends only on the difference between S and Y, and remember we already did note the difference between S and Y, S minus Y is tau, right? If it's a even more specific form, saying that it's actually a function of the L2 norm of the distance of the difference between S and Y. Then we call it a isotropic kernel. So here we have this is kernel, right? This is kernel, and inside of it we have stationary kernel, right? Stationary kernel, and inside stationary kernel there's a subset called isotropic kernel. Okay. Isotropic kernel, and the RBF kernel that we talked about is one special case of isotropic kernel. Right? Is here. Okay. And there is a lot of other kernels besides the RBF kernel. So we have the circular kernel, spherical kernel, and rational quadratic kernel, exponential kernel, Gaussian kernel. Gaussian kernel is actually exactly the same as, so this is just different name, right? Like Gaussian basis function and radial basis function, they're the same thing basically. And Gaussian kernel, RBF kernel, basically the same thing. With the wave kernel here, so we have different kernels, right? So let's look at a few of them. For the Gaussian kernel is here. So naturally it has a Gaussian shape, right? It's a bell shape. If it's a wave kernel, then this is kind of like the wave function in signal processing. And exponential kernel, the difference between exponential kernel and Gaussian kernel is that this is, in Gaussian kernel you have a square of the L2 norm, right? And then exponential kernel you don't have it. And here, if you look at exponential kernel, it's actually more peaky. It's really more peaky in the middle. And these are all the other kernel functions. Okay. So you can actually choose different kernels for different problems. Okay. So next we're going to talk about a few concrete kernels and kind of briefly analyze some of its property. So if you go to square exponential kernel, so this is the Gaussian kernel, right? The reason why it's called square is that you have a square of the L2 norm. So this is again the Gaussian kernel, and it's also equivalent to the RBF kernel. Right? And if you look at this kernel, and if you compute the spatial density of the kernel. The spatial density looks like this. Okay. So S, again, S is the frequency. S is the frequency. And big S of small s is the magnitude for each frequency. You can see that there's actually no the imagery part in this complex number anymore. Right? It's just something like this. Okay. This is square exponential kernel, SE kernel, and it has different names. You can also call it RBF kernel or Gaussian kernel. Okay. And there's a generalization of square exponential kernel, which is Matten kernel. So Matten kernel has a kind of like a more specific and more involved form. It looks like this. So, and by the way, let me just to make things easier. So just to remind you that R here is the L2 norm, right, between S and Y. Okay. So here, this is the Matten kernel, and Matten kernel, if you has a very special parameter called nu. So this is a Greek letter, looks very much like V, but it's called nu. So nu is when you take nu into infinity, then this Matten kernel will approach the SE kernel. Okay. So instead of setting it to infinity, if you set it to other value, for example, set it to 3/2 or 5/2, and this is what it looks like. If you plot it on a figure, let's say that you choose several different nu. You choose nu to infinity, choose nu to 2, and choose nu to 1/2, and you plot them. Basically, you plot k of r versus r. Right? K of r is the value of the kernel function. R is the L2 norm, right? And it looks like this. You can see that when nu is infinity, this thing is basically is very similar shape. It's exactly the same shape correspond to some of the SE kernel, right? And then if you can also plot some of the functions that is suitable to be approximated using these kernels. So you can see that if you can actually plot the function that's suitable to be approximated by the case where nu is equal to infinity. It looks like this. If the data, the ground truth model, if the ground truth model looks like this, then it will be best if you set the nu to infinity or directly use the SE kernel. Right? If your data instead looks more like this, so it's less smooth, there is some ups and downs, right? Then it's better for you to choose a slightly smaller nu, for example, set nu to 2. If your data is highly oscillated, something like this, then it's better for you to choose a smaller nu, like 1/2. Okay. So one question is how do we generate? So how do we plot this? Right? Someone might be wondering. So the way we plot this is that we first choose a kernel. We choose a kernel, and then we sample the data equally spaced between -5 and 5. For example, between -5 and 5, we sample 200 data points. Sample 200 data points in here, and then we can compute the corresponding f of x. How do we compute this? The way we compute this, if you look at our original equation, right? In the original equation, we say that this y of x is equal to the inner product between w and phi of x, right? And this w here is equal to what? This w here is equal to A transpose times the feature matrix, right? A transpose times the feature matrix. And then from this, we say that this product between the feature matrix and the specific feature can be kind of denoted or rewritten as the boldface k, right? Boldface case of x. So here the boldface case of x is a vector, and the first entry of the vector is k of xx1. The second dimension is k of xx2. Okay, so this is an n-dimensional vector. So here you can already kind of see how we can plot the function. We first choose a kernel, and then if we have the kernel, we sample equally spaced data. We sample a lot of x, and then we can compute this part, right? We can compute this part for any x, right? And then we randomly generate some vector a. So with this we already get a and k of x, right? Then we can plot the y of x for any x, and this kind of gives us this figure here, right? And this is how it's generated. But what this figure tells you is what kind of data is suited for what kind of kernel. If the data is highly oscillatory, then it's better to use a smaller nu. If the data is smoother, remember we are trying to do the regression task. Okay, if the data of y versus x is kind of smoother, then it's best to have a larger nu. Okay. Any questions so far? Okay, so this is the Matten kernel. It's a generalization of SD kernel. Okay. So another kernel that we can discuss is the special case with Matten kernel with nu equals to 1. So if nu equals 1, it actually becomes what? It becomes the exponential kernel. So this is exponential kernel. This is like the Gaussian kernel, but instead of the square, it just have the simple r here. And the Gaussian kernel, in the exponential kernel, we're not going to talk about the plot for exponential kernel, but we're going to talk about another generalization of that can kind of include both the exponential kernel and Gaussian kernel. So this is called a gamma exponential kernel. So the gamma exponential kernel looks like this. So this is basically the e to the power of minus r over L. Remember, the L is that the variance that we set. R over L to the power of gamma. Right. So if this gamma equals to 1, it's going to be the exponential kernel. If gamma equals to 2, then it's the square exponential kernel or Gaussian kernel. Right? And then we can actually plot. We can plot the kernel value. So this is the kernel value versus R. Right? We can plot the kernel value versus R in this plot, and we can plot it for different gamma. Right? So for gamma equals to 2, this is gamma equals to 2, the green line, right? Again, exactly like the Gaussian shape. And if gamma equals to 1, it's more peaky, right? It's the exponential kernel. And if gamma is equal to 1.5, then it's kind of like in between. Okay? And then you can, similar to what we have been doing, we can plot what kind of function is suitable for what kind of kernel. Right? We can plot fx versus x. Again, we're going to first sample x, equally spaced x, like 2,000 points between minus 5 and 5, and then we're going to compute the kernel, and we're going to randomly sample the vector a, and we generate this plot. Okay, so if you look at this plot, you can see that again, if your data is smoother, then it's better to set gamma equals 2. If your data is like more oscillating, then you're gonna it would be best for you to choose a gamma that's smaller. Okay, so this is another general kernel, gamma exponential kernel. Okay, Any question for this kernel? Cool. Another kernel is, we call it rational quadratic kernel. So basically, you can think of this kernel as a infinitely weighted sum of SE kernel with different length scales. Something like here. So basically, it's like if you look at the exponential kernel, here you have a length scale, right? But one question that you have is that if you decided to use the SE kernel, what kind of length scales should you use, right? This is a hyperparameter. But instead of choosing a hyperparameter, why not just have a lot of SE kernels with different length scales and add them up? And this is exactly rational quadratic kernel. Right? And if you add them up, you actually happens to have a closed form, which looks like this. So one question is that even if you choose to add them up, you kind of introduce another set of hyperparameters, because it kind of depends on how you add them up, right? So you're not going to add them up quite like equally weighted. For the kernels with different length scale, you might have different weight. Right? So you kind of have introduce another hyperparameter, L and alpha. And here we try to plot the kernel value, basically the K of R versus R, if you fix L to some value and choose alpha to different value. So basically, if you choose alpha to infinitely large, this is what it looks like. If you choose alpha to be smaller, then it's going to look something like this. Okay. And again, you can plot fx versus x. So basically, what kind of data is suited for what kind of kernel. This is different. This is the plot for different alpha. Okay. And you can see that this, in this case, is not very much different. The only difference might be if you have a larger, like closer to infinity alpha, you can still kind of see that it's smoother, right? And if alpha is smaller, then it's kind of like you have more ups and downs. But it's kind of much better, already much smoother than the kernels that we have been seeing like this, dramatically oscillating. It's not like that. It's kind of like still very smooth, slightly less smooth. Okay, so this is rational quadratic kernel. Okay. Any question for this kernel? Okay. So we can kind of see that different kernel corresponds to different kind of data, right? And another kernel, probably one of the last kernel that we're going to discuss, is piecewise polynomial kernel. So what's piecewise polynomial is that if you the kernel value will be cut to 0 after some point, basically, or it's like a piecewise polynomial. It's like for this segment it looks like for this segment, it looks like some. For example, for this kernel for this segment, it will look like minus x squared. Right? But for this segment, it's gonna look something like minus x plus 1. And for another part, it's gonna look like another polynomial. For example, it's gonna look like x minus 2 squared plus 0.5, something like this. So this is like piecewise polynomial, and we can have different piecewise polynomial kernels. So in this piecewise polynomial kernel, we have one very important hyperparameter, which is q here. So q, this is basically kppd comma q. Right? So q, if we say that we have a piecewise polynomial kernel with parameter q, then that means we need a polynomial kernel that is 2q times continuously differentiable. Okay. So concretely, if we have a piecewise polynomial kernel with q equals to 0, then it's going to be something like this. So this is 1 minus r to the power of j. And what's important is the plus sign, right? In the subscript, the plus sign basically says that if, let's say 1 minus r, right? 1 minus r plus sign means that if you have some r, if this r is too large, so large such that 1 minus r is smaller than 0, then you're just going to directly set it to 0. Okay. So if you're familiar with neural network, then this is like the ReLU function. Right? If it's smaller than 0, then you just directly set it to 0. And j, you're going to set j as d over 2 plus q plus 1. So d is another hyperparameter, just to decide on the order of things. Okay, and this sign, this is the kind of like you just take the floor of some number, right? For example, 3.5. The floor of 3.5 is 3. Okay, and the floor of 2.5 is 2. Okay, so this is to make sure that this is a integer. Okay. So this is the piecewise polynomial kernel with parameter q equals to 0, and as q kind of gets larger and larger, because you need to make sure that it's 2q times continuous differentiable, the form kind of gets kind of like more and more complicated, right? So this is q equals 1, q equals 2, and q equals 3. Okay. Now if you plot the kernel function for different hyperparameters, we have 3 cases. The first case is d equals 1, q equals 1. The second is d equals 3, q equals 1. The third one is d equals 1, q equals 2. Okay, so you plot them. The kernel looks like this. Okay, and you plot the fx versus x to see how it looks like. Basically, just to see what kind of data is more suitable to what kind of hyperparameters. It looks like this. So you can see that if you set q to larger, it's kind of like more it's higher order differentiable. Right? The fact that it's higher order differential means that it's kind of smoother everywhere. There will not be some kind of like very peaky change. Right? But if you set q is equals to 1, it's often the case that there will be some abrupt change, not very smooth, abrupt change. So this is the intuition for different hyperparameters for piecewise polynomial kernels. And one interesting property of piecewise polynomial kernel is that it tends to give you sparse grand matrix or sparse kernel matrix. This is because you have a cutoff point, right? Because if it's going to get 0, it's going to become 0 once r is larger than some value. Right? Once r is larger than 1, then this whole thing, this is going to be 0, and this whole thing is not going to be matter anymore. So basically, what it says is that because r kind of measures the distance, right, between x and y. So if the distance between the two data is too far away, then the kernel value will be directly set to 0. Okay. Any question for this part? Sometimes it can be very helpful if you use this kernel because you have a sparse square matrix, and computationally it can be very, very time saving. Questions so far? Okay, so this is piecewise polynomial kernel, and if you look at what we have talked about, there is a constant kernel, there's a linear kernel. Linear kernel basically is our inner product kernel, right? This is without doing any transformation. You just directly take the inner product of two input vectors. So this is linear kernel, and you have some polynomial kernels. Just take the inner product and then raise to the power p. You have the SE kernel, which is what I've been talking about. You have Matten kernel, a generalization of SE kernel. You have exponential kernel. So you compare these two, square exponential. It's called square exponential because it's the square of the exponential kernel. Right? So and you have this gamma exponential, which is a generalization of both the square exponential and exponential kernels. Right? You have an additional parameter gamma here, and you have the rational quadratic kernel, which looks like this. And the last one we're going to talk about is neural network kernel. We're going to leave this to the end of the class if you have time. So if you have a neural network, you have a two-layer neural network. Basically, you have only one hidden layer. You have a linear layer and nonlinear activation, and then another linear layer to do the final regression. The kernel function is going to look like this. Okay. And whether or not they are stationary, if all we have talked about the first 5 kernels, they are stationary. Constant kernel is also stationary. Okay. Any questions so far? Okay. So the next question I'm gonna talk about is if we specify some kernel function, okay, can we go back and figure out what kind of feature mapping that we're using? If it's the forward case, if given the phi, then we can very easily figure out what's k, right? But given k, can we go back and figure out phi? So this is the question that we're going to talk about. So before doing this, we're going to discuss a notion of eigenfunction for kernels. So we're going to define the eigenfunction of a kernel k as something like this. So basically, any function phi that can satisfy this equation would be an eigenfunction for kernel k. You might find this look very familiar. Right? Basically, this is going to be in the integral. It will be k of x and x prime times phi of x. Right? This is x. This is x prime. This is x. Right? And you're going to take the integral over x. So after you take the integral over x, all is left is x prime, right? It's going to be some function of x prime. And this function of x prime is going to be the product of lambda is a scalar value, times phi of x prime. Right? So this phi and this phi, they're the same phi. Right? It's just different input argument. So if you look at this, you're going to find that, and again, lambda is the eigenvalue. Right? Lambda is the corresponding eigenvalue, and phi of s is the eigenfunction. So if you compare this to our traditional way of defining eigenvectors, the traditional way of defining eigenvectors looks like this. So basically, given the matrix K, and we're going to define an eigenvector of the matrix as any eigenvectors that can satisfy this equation. Right? K times V equals to lambda times V. V will be, if this is happening, then V would be our eigenvector. The corresponding lambda will be our eigenvalue, right? And for a matrix, there can be multiple eigenvectors, right? And correspondingly, there will be multiple eigenvalues. And if you look at this, this is actually a continuous generalization of this kind of eigenvalue decomposition. Right? For a kernel function, there will be multiple eigenfunctions, and correspondingly, there will be multiple eigenvalues too. Okay. In fact, you can kind of discretize this one and make it look like this matrix eigenvalue decomposition. But we're not going to talk about this. So just put it here so that we can see the analogy here. Basically, given a kernel function, you can perform eigenvalue decomposition too, and you can get the eigenfunction and the corresponding eigenvalue. And there is this famous theorem that says that given a kernel function k, and if you can get all the eigenfunctions of the kernel function, then the kernel function can actually be represented as the sum of infinitely many terms, where each term is actually lambda j times phi j of x times phi j of z. So this phi j of x is the jth eigenfunction, right? It's the jth eigenfunction for this kernel. Right? So this basically gives you a way of basically factorizing this kernel function, factorizing this kernel function into the sum of a lot of inner product, basically sum of a lot of terms, and you're going to see that this actually corresponds to some kind of inner product. Okay. If you look at this, you can actually rewrite this whole thing. You put the lambda j into the product of two square root of lambda j, and you give 1/2 to the left and give 1/2 to the right, right? And then you're gonna see that you can actually rewrite this sum as something like this. Right? You can set let me write it on the board here. You can set this lambda j times phi j of x as this is another Greek letter called psi j of x. So basically, this will be your feature map. You can think of this as a feature map, right? Correspondingly, let's say that given this kernel function, this whole thing, the corresponding feature map will look like this. So this is going to be equivalent to taking the inner product between lambda 1 times, we're going to use this phi 2, lambda 1 phi 1 x, and second term is lambda 2 phi 2 x, right? All the way to infinity, basically, all the way to infinity. You have a lot of terms. You have infinitely number of terms, and for the z part, right, for the right hand side, this part, right, you have something that's similar. You have lambda 1 phi 1 z, and lambda 2 phi 2 z, all the way to infinity. So that basically gives you the corresponding feature map, right? if you use given some kind of kernel function, after the eigenvalue decomposition, you can then find the corresponding feature map, and this is the corresponding feature map. Okay. And if you look at this, this is our example in the very early on, an example where we use the RBF kernel. This is RBF kernel, and RBF kernel can also be written in this form. And if you look at what we have done is that we kind of decompose this RBF kernel using Taylor expansion. We can decompose it into the sum of a lot of terms, right? And then we say that this is actually equivalent to the inner product between two vectors, of this vector and this vector. Right? This is exactly the same thing. Right? We're already doing this eigenvalue eigen decomposition, right? And correspondingly, this is the same in the case here. Only in here it's more general, but in this lecture we're not going to talk about exactly how you do eigenvalue decomposition for a kernel matrix. So for now, you only need to know that if you finish the eigenvalue, the eigenfunction decomposition, you can use the eigenfunction and eigenvalue to figure out exactly what is the feature map corresponding to each kernel function. Okay. Any questions so far? Okay, so this is how we can obtain the feature map given a specific kernel function. Okay. Next, we're going to talk about a related topic. So this is another class of kernels. This is translation invariant kernel. So this translation invariant kernel is you think of it as a more general case, special case of stationary kernel. So again, the kernel value will depend on the difference between S and Z, but the value will be only defined on a bounded area. So it's going to be defined on 0, for example, 0 to 2 pi, and then it's going to be extended to the whole real space. And a typical example of translation invariant is this one. If you look at this example, you're going to see that this value, first of all, n is an integer. Okay, a is an integer, and if you look at this one, you're going to see that this is actually the input space is actually depending only on 0 to 2 pi, right? Because after 2 pi, if you go from 0 to 2 pi, everything will be reset, and the rest of it will be repeated of the first part, right? So this is an example of translation invariant kernel. And if you look at the cosine here, remember that this u, again, this u is what? The u is the difference between S and Z, right? And you can actually decompose cosine of the difference between S and Z into two terms, right? Therefore, k using this cosine kernel, and this k of x minus z will be equal to a0 times this part, right? Times this sine part, and plus the sum of infinitely many terms of this first part, the cosine part, right? And if you look at this, you can actually see that the corresponding feature map will be something like the first dimension will be square root of alpha 0, a0. The second dimension will be the square root of a1 times sine x. The third term will be square root of a1 times cosine x, right? All the way to infinity. Right? if you, let me write it in a board so that it's clearer. If you look at this one, so this is phi of x, right? And correspondingly, you have the phi of z. So the phi of z is something like this one, and the second dimension of a1 sine z and a1 cosine z all the way to infinity. Then if you take the inner product, you will take the inner product of phi of x and z of x, right? This is going to be phi, the square root of a0 times square root of a0, right? plus a1 sine of z times a1 sine of x, right? And plus a1 cosine of z and a1 sine of x, right? all the way to infinity. And if you look at this one, this is the first term, right? This is a0, right? And if you look at this term is actually when the first term of this summation, when n equals to 1. Right? And similarly, this term, sorry, this is sine, this is cosine. Cosine. And the third term, right? The third term is corresponding to this one, right? When n is equal to 1. Okay. So given some kernel function, sometimes you can directly decompose it, right, into the sum of infinitely many terms, and then you can immediately figure out what's the corresponding feature map. Okay. Question so far? Okay, so this is translation invariant kernels. And we can talk about perhaps the most general case. The most general case is that if you recall Bochner's theorem, in Bochner's theorem, it tells you how to decompose a stationary kernel into the sum, basically the integral, right? The integral of different terms. So here you can think of this as the sum of infinitely many terms, with each term having a different frequency s, right? So this is actually very similar to our eigenvalue decomposition. If you rewrite this one, you can actually rewrite this one as something like this, right? So this star here is the conjugate of a complex value. Okay, so you rewrite this one as this one, and then you can figure out that the exactly explicit feature map is actually it looks like this. This is the feature map for each dimension. Specifically, in the feature map, for any of this stationary kernel would look like something like feature of s, or something like this. Square root of p of. So we say that this frequency will go from let's say that the frequencies going to go from 0 to all the way to infinity. Okay, so this is going to be 1 and 2 pi I s x. So this s is going to be, in the first dimension, it's going to be 0, and So this is the first dimension of feature map. And the second dimension of the feature map is gonna, for example, it's gonna be something like this, times 1 times x, right? And all the way to infinity. Right? So we can think of it as a feature map that looks like this. But in practice, as is actually, it's not an integer. Here we assume that as is an integer, but in practice, as can be, for example, a real value. Therefore, this whole thing, this whole feature is actually a continuous function. Again, like a very densely populated a vector. Right? For now, for simplicity, you can think of it as just taking as an integer frequency. Therefore, the feature map corresponding to any stationary kernel can look like this. So this is the first dimension, the second dimension, all the way to infinity. Okay. And again, this e to the power of 2 pi isx is a complex number, so it's equivalent by definition to cosine of this term plus I times sine of this term. Okay. So this is the most general way of figuring out what's the corresponding feature mapping given a specific kernel function. And there's another case. Another case is we're going to discuss polynomial kernel. So let's say that we're given the polynomial kernels. This is the polynomial kernel. The polynomial kernel will first take the inner product of x and x prime and plus some kind of hyperparameter r and raise it to the power of m. So this is polynomial kernel. Okay? And then we're going to ask the question of what's the corresponding feature map for the polynomial kernel. Basically, given this polynomial kernel, what's the corresponding phi of x? Right? We're going to discuss a special case. The special case is m is equal to 2. So if m is equal to 2 and gamma and r, they all equals to 1, what's going to happen? And again, we're gonna assume that this s is in the 2-dimensional space. Okay, so for each x, there are 2-dimensional. The x is going to be x1 and x2. Okay, so we're going to expand this. If we expand this, it's going to be 1 plus the product of the first entries of the 2 data points, right? S1 and S1 prime plus x3 and so prime. So this is the second dimension of both data, right? And you add them up, and then you take the square. You do this, and then you're gonna kind of expand this, right? This is the sum of 3 terms. You're going to take the square, so that basically will be 9 terms, and you can combine different terms, and this is what you get. Right? Basically, this is what you get. You have 1, 2, 3, 4, 5. You have 6 terms, right? 6 terms, and you will see that you can actually derive an explicit equivalent feature map that looks like this. This is the equivalent feature map. You can verify this at home. But given a input vector x, you're gonna compute a 1, 2, 3, 4, 5, 6-dimensional vector according to the first entry and the second entry of this vector. Okay. To briefly verify this, you can see that if you take the first entry, if you take the first entry for s and s prime, then it corresponds to the first term, right? And if you take the second entry for the x and s prime, it's going to be the square of the square root of 2 times x1 times x1 prime, right? So this is exactly here. And correspondingly, you can see the third term also corresponds to this term, so on and so forth. Okay. So basically, if you use a polynomial kernel with m equals to 2 in a 2-dimensional space, it's actually equivalent to expanding the feature into 6-dimensional space. So it's actually quite quite cost effective, right? Using this kernel, you can cheaply extend your feature map. The only thing you need to do is that you need to compute the kernel metrics, right? But you don't need to explicitly expand them. Okay? And if you look at the general case where, let's say that the kernel is taking the inner product of these two vectors and raised to the power of m. M is a general m. Then you're going to see that, sorry about that, this should be capital D, it should not be m. So we assume that each x has a d-dimensional, right? Then the corresponding feature map will have a lot of dimensions, and in each of the dimension corresponds to different configuration of MD. So this MD is M1, M2, all the way to M capital D, and each M lowercase d corresponds to the order of the D feature. Okay, so you have a lot of dimensions for this feature map, and each of which will correspond to a combination of MDs. Okay, and for a specific configuration of MDs, you can compute the corresponding feature entry using this equation. The corresponding feature entry is the square root of the factorial of capital M. So M is this M here, okay, over the factorial of M1, M2 times all the way to the factorial of MD, M capital D, and times all these different terms. So x1 to the power of M1, x2 to the power of M2, all the way to xd to the power of M capital D. Okay. And you're going to have a lot of terms, and specifically you're going to have this many terms, right? So you can see that if you use a very high order polynomial kernel, it's equivalent to expanding the feature into a space that is very, very, very high dimensional. Okay. Any questions so far? And I hope that it gets clearer and clearer that why we're using this kernel, because the reason that why we're using this kernel is because by simply computing the value for each pair of data points, it's actually equivalent to expanding the input space to a very, very high dimensional feature space. So this is actually a very, very cost effective and very cool idea. Okay. So this is polynomial kernel. And next we're going to very briefly talk about neural network. So what's the corresponding kernel if you consider a neural network? So here the neural network, we assume a very simple neural network. This is the input, and the input will go through a linear layer to get a hidden unit, and you're going to have some kind of nonlinear element-wise transformation. And then you're going to go through another linear layer to produce your output. Right? So this is your first layer. The first layer is h of x and uj. Uj is here. It's a layer for the first weight. It's a weight for the first layer. Right? So this computes the jth hidden units of the neural network, and this whole thing it's a sum of nh terms. So it's basically the weighted sum of the nj hidden units. Okay, so it's gonna be a weighted sum plus some bias term. Bias term will be b. B is a scalar value. Okay, so this is a neural network. A neural network, and we can, if we assume that. First of all, let's assume that this we're going to draw the bias from a standard Gaussian distribution with the Gaussian distribution with zero mean with some standard deviations sigma b, and we're going to draw we're going to sample Vj here, right, from a zero mean Gaussian distribution with some standard deviation. If we do this, and let's consider another assumption. Another assumption is that the mean of these neural networks, if you randomly sample B, this one, and the parameters, the mean of this output will be 0. And with this assumption, you can actually compute the covariance for this. You can see that this is actually very similar to our this is very similar to what we have for the kernel function, right? This is inner product basically. It's like the covariance between a pair of input. So if you expand this, you can see that this is actually the expectation of this is actually equal to sigma b squared times the sum of j terms. J kind of indexes the hidden units, okay? And in each of the term inside the summation, there will be sigma square, sigma b square. So sigma b square is here, right? And it's going to be the expectation of u. And inside the expectation, there will be the inner product. It's not like the inner product. It's like just the product between the same hidden units from different input, right? So this h of x and uj is the jth hidden unit. For example, some hidden unit here, right, for the first data point, and this is the jth hidden unit for the second data point. So, and this one is that if you take the expectation over u, and what's the expectation of that product, right? You can kind of expand this into this one, and then you can go even a step further, because you're going to assume that all these u, they're going to sample from the same Gaussian distribution. Therefore, all the summation, all the terms inside the summation, they're going to have the same expectation. Therefore, you can simply take out this summation term, replace it with n sub h. Okay, so that basically gives you the expectation of the covariance. Basically, gives you the covariance of x and x prime. So this is the expectation. What's left is the u here, because you still need to consider what kind of expectation you're going to take. To generate u. So in the next step, if you further assume that u is generated from a Gaussian distribution with some covariance matrix, then you can actually compute what we have as something. We're not gonna talk about the exact procedure of computing this, but you only need to take a look at the result. The result is that the corresponding kernel for a neural network with a u that's randomly sampled from the Gaussian distribution looks like this. So this is 2 over pi times the inverse function of sine. So this is arc sine, and inside this arc sine there will be 2 times x tilde sigma times x tilde prime. So this x tilde, you can, for simplicity, you can simply think of x tilde as x in here, okay? And then it's going to over this whole thing. So I know this is a bit complicated, but the main idea here is just to such that you know that even if you have a neural network, then it's going to correspond to some kind of kernel function, and this kernel function is actually related to how you assume the last layer of weights, this generative form. If assume that your last layer weight is generated by a Gaussian distribution with some covariance matrix, and this covariance matrix will kind of has a very strong effect on the kernel, on the corresponding kernel for this neural networks. You don't need to know exactly how it's derived. It's just to have an intuition that exactly how the network is sampled is gonna affect the kernel function. Okay. So this is some very concrete example. If you assume that this U is sampled from some, assuming we have two-dimensional case, right? And assuming the U is sampled from a Gaussian distribution with zero mean and a diagonal covariance matrix with some fixed first entry, and let's say that we vary the second entry. What's it going to be? Right? If the second entry is set to 1 or 3 or 10, what's the corresponding neural network output that's going to be? So you can see that this is the three different cases. Right? If you set it to 10, then when the input is very small, the output is going to be very large, and there will be a geometric drop, and then go up a bit. But overall, you can see that what's the most unstable part is when it's around 0. Okay, so this is a neural network. Yeah, I guess we're gonna leave it here for today, and